Hello, everyone. Welcome to this virtual tour to the Paranal ESO Observatory. My name is Hernan Julio, and I welcome you to this great day. I hope you have a great day and a great virtual tour. My name is Hernan, and I am a journalist specialized in astronomy. So I hope you enjoy this tour. And also with us today is Felipe Zurita, who is uh, physics, and I want you to meet him. Hello, Felipe, how are you?
Hi, Hernan. Hi, everyone. My name is Felipe Zurita. I have a degree in astronomy, and I love sharing science and astronomy with people to you. I will be the Bruce this day in this online tour, and I am excited to help bring you this experience to you. So let's get started, Nan.
All right, let's get started. Well, we want to say hello to everyone who is watching us from anywhere in the world. We have just already have a comment. We have as well Graven from Amsterdam. Okay, and everyone else, please say hi to us. You can make your comment and your greetings in our chat in Facebook or chat in YouTube. So also your question, of course, the main idea is to make the most questions that you have. We will try to answer all of them. You know, in astronomy, there is a lot that we all have to learn. So let's start with this. And first of all, we want to introduce you to ESO. ESO is the European Southern Observatory. Okay, European Southern Observatory is international organization. Okay, has a member 16 member state. You in your right now in your screen you can see the 16 countries that are part of ESO. Even that most of them are in Europe, geographically talking, but they are not the European Union. Okay, some of these countries are not part of the European Union, so there's a different organization. We're ESO, the European Southern Observatory, and they are also we have a strategic partner, Australia. You can see it at your bottom right side. And of course, we also have Chile. Chile which is the host country, and this is skinny country which is in South America. Okay, ESO started in 1962 with just 5 countries. Okay, and after more than 60 years, okay, 62 years, now we're 16 countries. So let's see what is doing ESO. ESO is an international organization which is designed, okay, they build and operate telescope in the southern hemisphere, specifically in Chile. Let's take a look to the next slide where we will see which telescope are they built already and which one are they going to build, and which one are we building in Chile. Well, there you have the skinny long country in South America, Chile, and you can see the dark blue part are 2 regions in Chile where the observatories are, the ESO observatories are. First of all, we have in the southern part, or let's say northern southern part, or in the southern part of the Atacama Desert, was where La Silla was built in 1969, was inaugurated. La Silla is the first ESO observatory in Chile. It's about 500 kilometers north from Santiago. And we have 2 main telescopes there, the ESO 3.6-meter telescope and the ETT, the New Technology Telescope. We also have in La Silla, every Saturday, every 2 Saturdays we have also a virtual tour like this one. So if you want to get to know what La Silla is, how to get there, you just have to tune in with us next week and next Saturday. Also, it's in Spanish. This virtual tour are in Spanish and English. But today we have the English tour to the VLT of Paranal. And you can see that after we built La Silla in 1969, we started with the VLT. And the VLT is in the northern part of the Atacama Desert, in the Antofagasta region. Actually, the VLT, the Very Large Telescope, is about 120 kilometers south from Antofagasta, okay? And was finished in 2001. We started about 1993, 92, and we finished the VLT in the year 2001 with the last of the four big telescope, 8.2-meter telescope, okay, are over there. We will have a good and a nice look to what VLT and the VLTI are. Also in Paranal, we have the VST and VISTA, that are two survey telescopes. They are also in the Paranal Observatory. They are 4 and 2-meter telescopes. And of course, the most today big telescope that is we are building is the ELT, the extremely large telescope. Okay, the extremely large telescope is right now we are building the extremely large telescope in Armazones. Armazones is a mountain very close to Paranal mountain, about 20 kilometers to the east of Paranal mountain, and is going to be the biggest eye on Earth looking to the sky in the next decade. The ELT is 39.3-meter diameter telescope. Okay, as you can see from the 60s when we started, we were coming from 1-meter telescope to 39.3-meter telescope. So it's a big advance in just 62 years of history. And also we have you can see to your left bottom side, the CTA, the Cherenkov telescope array. This is a very special array of telescope. There's 99. They are not being built yet. They are already planned, and they are going to build it also very close to Paranal, very close to the ELT. Is going to be one of the biggest array in the gamma ray astronomy. These telescopes are very special because they detect the interaction of the gamma rays with our atmospheres. So as you will see, they don't need to have a dome. They're just a little bit like the radio telescope. And talking about radio telescopes, we're going now to Chagnantor, also in the northern part of the country, in the Antofagasta region, but to the east, in the Altiplanics, in Chilean Altiplanics. ALMA, the Atacama Large Millimetric Array, is the biggest radio telescope on Earth right now. It's about 5,050 meters above the sea level. Okay, it's a plateau. It's called Chagnantor. One thing is you have to know is that ALMA is not ESO. ALMA is another organization, but ESO is part of ALMA. It's a partner in ALMA with the North America, United States, also Japan. So it's a consortium of these three big organizations, and they design, build, and maintain ALMA. And also ESO has APEX. APEX is just one antenna of 12 meters, and this antenna is also in Chagnantor. As you see, we can see the whole battery of telescope that has been built by ESO in Chile, that we are building in Chile, and the telescope that we are part of them also, as in the case of ALMA. All right, we have some greetings also from Andrei Popov. Hello, everyone from Russia. Well, welcome. We have two Russian visitors last Saturday in Chile. Also, Paolo Gapetti is with us. So thank you very much. Please don't forget to leave your message, leave your greetings, and also your questions in the Facebooks and the
YouTube. And
we
YouTube.
have Jose Maria also, great in Paranal team, and to the rest of the world. Well, thank you very much with us. Let's enjoy this, and well, let's start. Let's take it. Let's take a fly to Paranal and see how it looks like. Well, first of all, we are flying over the desert, the Atacama Desert. The Atacama Desert is one of the driest deserts in the world. Okay, it's about 5% of humidity. 2 weeks ago, I was there in the heart of the Atacama Desert. Very hard weather, hot in the day, very cold in the night. And here is where we have the best sky in the world for looking to the stars. And the ESO Observatory decides in the 90s to build in this mountain, the mountain that we're getting close to now, the Paranal Mountains, to build, which is today the most advanced astronomical machine in the world, the VLT and the VLTI. You can see that in the background of the image, you have some DC or clouds. Actually, there are clouds because we're about 12 kilometers in a straight line to the ocean, to the Pacific Ocean. Okay. Here we are just in the Paranal, looking to the Paranal mountain from above. And let's go to down and to see it closer, to take a closer look to the Paranal mountain. Here we are. Here you can see the VLT and the VLTI machine. The VLT are the four big telescopes. Okay, they are 8.2 meter diameter each. This is the most advanced machine in the world, and we call it UTs. And these four machines at the four telescopes are the same inside and outside. But also we have the small ones that you can see there. We call them the auxiliary telescope, the ATs. The auxiliary telescope are 1.8 meter each, and they are the interferometry, what we call the VLTI interferometry. This is the whole platform that you can see from drone flying. And now we will go down to take a better and closer look to this. We change view, and here we are at the Paranal Observatory, in the Paranal platform. Let me give you a nice view of where we are. We are in the heart of the Atacama Desert. As I told you, over there behind us, in the background, we can see this clouds. Those clouds are over the Pacific Ocean, and they stay there because we have a very special condition, atmospheric condition here. Is because we have the Humboldt current. The Humboldt current is a cold current. It's coming from the Antarctica, and that Humboldt current produces that the clouds don't go up over 1,000 meters. Here in the top of the mountain of Paranal Mountain, we are at 2,600 meters. So that's why we have also this very beautiful and gorgeous blue sky in the day, and we have 300 clear nights in the year, per year. And this is a view. We're looking to the east now. Let's have a look to the east, to the mountains, to the far mountains are the Andes Mountains, okay? Right there is the Andes Mountain, those very far away. The closer mountains are what we call the coast mountain range, okay? And the last one in the background, very far away, are the Andes mountain range, okay? Actually, we here have, we're looking to Armazones. This is the site, the ELT site, where we are building this extremely large telescope. Actually, it's already more than 50% of the contraction is already ready. And I was there a couple of weeks ago, and it's amazing. You just looking from the far away, you see this enormous cathedral, astronomical cathedral. It's really amazing. So we invite you to come soon in the next year to get to know the ELT and of course the VLT. The VLT, you can visit it every Saturday at 8 o'clock, 10 o'clock in the morning, and at 2 p.m. in the afternoon, every Saturday of the year. So you just have to book in our webpage. You will find the link, and you can book your visit every Saturday. We will be pleased to have you here. Please, if you can, remind us that you came and that you already took this virtual tour with us also. This is the VLT, and first of all, I want to tell you that this telescope that you see here, this enclosure, we don't call them more domes, this dome or enclosure, they have named, each of the telescope have a name. This is the Antu telescope. Here we have the Kuyen, the Melipal, and the Jipun. They are Mapudungun names, the names from the inhabitant from the southern Chile, the Mapuches, and that means sun, Moon, Southern Cross, and Venus, okay? As I told you before, the four telescopes are the same inside and outside, okay? And we will visit one of them, but before that, I want to show you also the ATES. Remember, these small telescopes are the auxiliary telescope. They're very special. Inside of the telescope, we have a 1.8 meter diameter mirror. Okay, and these mirrors, this telescope, excuse me, they move in this railroad. Okay, you can see the railroad here. Let's take a closer look. See, you can see the railroad here, and you can see also this tap. Okay, here there is a hole in this white and red tap. There's a hole, and what we do is we move the telescope through this railroad like a train, and we and they take position in each. They can take position in each one of these um, taps or holes. Okay, because what we do if we take the telescope, we open the telescope in the night, and we look with two or more of them to one star, doing what we call interferometry. I think the best way to explain what interferometry is through the video. Let's run the video, please, Felipe. There we go. You can see the four big one telescope. They're open, and we are looking to the same star, and we create a virtual mirror of 130 meter diameter. When we use the four small one, we create a virtual mirror of 200 meters. Now, the first thing is to let you know that when we talk about 130 meters or we talk about 200-meter virtual mirror, doesn't mean that the mirror get that amount of light. Okay, it's not like to have a 130-meter telescope getting the amount of light equivalent to a 130 or 200-meter mirror. These mirrors are virtual, and what they do is they give us the let's say the finest look to the image, or in other way, what we call the resolution or the details of the image that we're looking at is equivalent to 130, excuse me, or 200-meter mirrors. Okay, so how we do that? Well, we first of all we have to point the telescope to the same star. You make interferometry when you point two or more telescopes to the same star. When you do that, for example, in this case, if we take the four big ones and we point them to the same star, the difference between the first one and Japan is 130 meters. So we create a virtual mirror of 130 meters. In that way, what we do is to have this mirror, and we have details, very fine details of the object that we're looking at. If we can run one more time the video, please. There we go. And same thing we do with the small telescope, okay, with the ATES, with the auxiliary telescope. We take those four small telescope and we put them in different positions, and then we make this 200-meter. We can make two 200-meter telescope virtual mirror. And the same, we can get very fine details of the object that we're looking at. So that is what we talk about VLTI, or Very Large Telescope Interferometric. All right, let's go then to one of them. Let's go inside of one of them. No, before that, I want to show you something that I cannot show you in if you can in day tours. We cannot do this. We cannot go to the underground tunnels. See, the light from the telescope goes through underground tunnels to the center part of the platform where there is a building. Well, we are underground that building. This is the underground tunnels, is where the light travels, okay? Because when we take the light from the telescope, okay, it's the beam of light that travel through these tunnels in order to get together at the same time, at the same nanoseconds, to create that that mirror, that virtual mirror. So this is the tunnel where the light travels. In the day, when you come in Saturdays and visit a tour, guided tour visit every Saturday at 10 o'clock in the morning or 2 p.m. in the afternoon, you cannot go inside of the tunnels because it's a clean room. Only engineers can do that. But thanks to technology, I could show you the tunnels. All right, so hopefully you come to Chile soon enough to get to know Paranal. Let's go inside of the telescope and let's see from inside. Let's go to UT3 of Melipal. Here we are. We're at Melipal inside of the dome, and you can see how huge is the telescope. Let's take a round look, a 360 degrees look to this telescope so you can get the feeling of what is to be inside of the dome. You can see this engineer are working here. Of course, the picture that this 360 picture is a picture taken in the day. Nobody can work at night inside. The astronomer work in the control rooms, and this engineer and working in this instrument. But first of all, let's see. I don't know if we have any comments. Somebody, Kavidu Chat Uranga Sakai, saying hello. I don't know if I pronounce right or no. Well, welcome to everyone that is online. And if you have any question, please, it's time to make the question. And Felipe and I will be pleased to answer to you.
That's right. Remember, you can leave your questions about astronomy, the tour, the virtual tour, wherever you want about the astronomy or the space. So leave your comments, greetings. So this, what is this part, Hernan? What is this? This.
Okay, let's continue. First of all, let's see how we look to the stars. Well, first of all, we have it's same at your house. If you want to open, you want to see the star in the night, you have to open a window. When we open a window here, we call the opening part. This is a door. It's a slicing doors. We open the door to the size, a slicing door, and then goes all over to the half of the roof up here. So we open all this part, okay, where this white thing here is what we call the wind chills. Okay, there's a wind chill. We protect the telescope from the wind in case that when in the night when it is open, and if there is a wind, we can use this wind chill in order to not let the wind to move the telescope too much. Okay, so when it is open, the light goes inside to the main mirror. The main mirror is right here. This mirror is 8.2 meters in diameter. It's reflecting the light to the secondary mirror right here, and from the secondary mirror goes down again to the instrument. Okay, here we have one instrument which is hanging from the telescope. It's called Cassegrain instrument, and also we have other instrument but the side, what we call Nasmith instrument. Here we have one of those instruments, Nasmith instrument, and the instrument is that the one who catch the light and send the information to the control room. But I think it's we have a video also where we show how the telescope gather the light from the stars. Let's run the video, please. Here we go. So we open the telescope and the light goes to the main mirror that I just showed you. The main mirror has an aluminum layer who reflects the light to the secondary mirror. There we go, secondary mirror, and then back to the sides, one side or to the other side, because there's a third mirror in the center that sends the light to the right or to the left, to the right or to the left. Or the light also can go through the mirror, through the tube that is in the center of the mirror, and go to the Cassegrain instrument in the back, in the bottom part of the telescope. That's the way how we get the light and how we send the light to the instrument. Okay, the instrument, we have three instruments as you saw in the video, two in each side and one in the bottom. And these instruments are very special because the instrument make the whole job. A long time ago, astronomers had to use their eyes to see through the telescope with their own eyes. Now we have the instrument which take the information, which got the information, the photons of light, and translate. Actually, we have a CCD inside who translate the photon to electrons. We send the electron, the data, the scientific data to the computer room where the astronomer is receiving that information, and of course also the telescope instrument operator is controlling the telescope to send the telescope anywhere in the world, in the universe. So this is an instrument. This is a visible instrument. We also have different instruments today. The technology help us, and we can see not only visible light, but also can see, for example, infrared or ultraviolet. In this case, this symphony is infrared instrument. Also, by the way that we are down here, let me show you this. This is what we call the main mirror cell. Okay, the mirror is over this cell. We will go up to see it also. And this mirror has this boxes that you can see here. Those boxes has actuator. This actuator push the mirror up and down, okay, in order to keep always the surface perfect. The mirror, as you will see now, let's go up again. The mirror is what we call flexible, okay, because it's very thin. You can see the mirror right here, okay, in this close-up. And this is the mirror. As you can see, the mirror has this aluminum layer which reflect the light, and the mirror has underneath the mirror, as I showed you, this actuator that push up the mirror in order to keep always the surface perfect. Because the mirror is so thin, it's only 17 centimeters thick and 8.3 meters in diameter. So when we move the telescope in the night, the mirror could change its shapes. So when that happens, the computer detects the nanomillimeter mistake or error and correct it on real time. So we always have a surface perfect, a mirror surface perfect. That is called active optic. Active optic, okay? And don't get confused with adaptive optic, because not in this case, not in this telescope, but in telescope number 4, we have adaptive optic. What is adaptive optic? Well, as I told you, we are in the best place on Earth for reach the light from the star. Crystal clear sky. But anyways, always we have an atmosphere anyways. So that atmosphere is very dry, so that's why we have very good sky. But anyways, it has some atmosphere. We have atmosphere, and always there is some distortion. When the astronomer wants to see an object perfectly, we use adaptive optic. For that, we need to have a very bright star, and because there is not everywhere in the sky a very bright star, what we do is we produce our own bright star. How we do that? We send a laser to the sky, 90 kilometers in the atmospheres, and over there we create a virtual star, an artificial star. With that star, the instrument, and a special instrument like this one, take the information from that star and the distortion that the atmosphere produced to that laser guide star, and we correct the distortion that the atmosphere produced to our scientific object, the real scientific object that we are looking at. In that way, we have very, very clear pictures. It's like looking to the star without any atmosphere. It's like to put the telescope in the atmosphere, over the atmosphere. That is called adaptive optic. So don't get confused. Adaptive optic and active optic. All right, we should make a quiz later on to our watcher to see if they understood this. But let's continue. Or there is any question, Felipe?
The common question have about the telescope is how far can see it.
How far can I see? Well, the telescope actually. Well, first of all, we have to see that we are our so far as far as we know through astronomy and science, the universe begin in 13.7 billion years ago. Okay, so that's the age of the universe. 13.7 billion years. And the first billion year was dark, no light, because the universe was a soap of particles. But after 1 billion years, the first star were created, and then the light was, and what's a light? So we can say that with this telescope we can look at 12.7 billion years in time back. Okay, because we are getting the light from those first galaxies. So we usually say when we use a visible instrument that we are looking to the whole visible universe so far. But everything is changing with the new telescope. We don't know what the ELT will bring us. So this is what we can say so far about the universe and about how far we can see. Let's continue because the time passed quickly by, and we will get out from the telescope, and we will go back to the platform. Okay, and now I want to invite you to where the astronomer work. Okay, also in the day we are not allowed to take people inside of the control room where we go in control building. um, Usually we walk, or the people get out of the telescope, walk all this platform and take a look, can have pictures. It's amazing. It's amazing. Visit every Saturday. So I insist that if you can come to Chile, please come and visit us. Well, let's go to where the astronomer work. I think that the best person for to talk about the control room is Felipe, who has a bachelor in physics and astronomy. So, what the astronomer do in this place, Felipe?
This part, in particular part of the observatories, is a part of the magic of the astronomy do. We have in this place we have two different kind of people. The ones is operator of the telescope because we need people move the great machines to see the skies, and the other people usually in normal clothes or color clothes are the astronomer, the busy astronomer. Every week and in every year, um, the astronomer moved to use this telescope every night. I mean, one astronomer, and I need to see a one star in particular. So I do a proposal for sent to the ESO HQ in German. So I prepare for use this in particular Paranal. If I need to use Melibal, I need to do a proposal about to use Melibal for C2 star. So I send that proposal, and later, if ESO agree my proposal, I come to Paranal and sit down in this part and work together the telescope operator. So this is the whole cycle of work in this. So in the night, I I captured a different information about my object, my celestial object, and later. come with my all data and to my university or scientist organization or any part to work to astronomy about astronomy. So this is the principal work here. This is the part of magic of the astronomy.
All right. Thank you very much. Also to say that we have two way of observing. We have a mode, observing mode. We have the classical mode when the astronomer that were Felipe was talking about means that the astronomer have to come to Chile and sit here and do the observation for himself. And also we have the classical, that's the classical mode. And we also have the service observing. The astronomer do not have to come, and some astronomer from our organization make the observation for him, and we send all the data. We save all the data actually in Germany, in our archive in Germany, which is in Garching. So any astronomer can log in that archive and get the information that he needs. Well, I think it's time to let our watchers to see what are the astronomer discover in this telescope. I think we have a video where we have prepared the top 10 discovery with the ESO telescope in Chile.
Sorry for my late. I have a little problem. So here we are, the top 10 of the principal discoveries.
All right.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
All right, we're back again to the telescope platforms, and also I want to show you, the time is running by very quickly, something that we cannot do it also when you come every Saturday. This is a virtual tour. We can use the technology and show you how it looks like the sky at night or sunset in Paranal. You can see here is this gorgeous view of the sky, and I will show you a little bit what we are looking at here. Well, you see in the night the telescope are open and waiting for the whole darkness. They start to look into the stars. This is called the opening, which happens every sunset. Before sunset, we do the opening. We open the telescope against the sun, of course, and the sun just set in Paranal. Also, you can see here the small telescope, how they are open, ready to look to the stars. And what we can see here is, I don't know, some of you are from the northern hemisphere, so you may know this constellation. It's called Orion. Okay, the Orion constellation, and we can see very clear here the Orion belt. Okay, here we have these three stars. Okay, are the Orion belt, and of course also this great image can show us in detail the Orion Nebula. It's where thousands of stars are burning right now in this nebula. It's a gas of dust cloud where thousands of stars are burning right now, and this is Orion. Orion is a mystic man or hunter from the Greek. This is we have to have imagination, of course. The head is here. It's upside down. Remember that we are in the southern hemisphere, so it's upside down. Here's the head. Then we have the Orion belt, one leg, another leg, one shoulder, another shoulder. Here is one arm, and this is the Orion constellation. Over the Orion constellation, we have what we call the big dog. Right here, you can see Sirius, which is the brightest star at night in the night sky. And you can see the dog here. It's the eye of the dog. You have the back, one leg, the tail down here, and another leg. As I told you, we have to have a lot of imagination for to see a dog over there. However, I want to show you the southern sky. So we have to move to the south. We will move to the south here with this picture, and you can see the Milky Way. It's amazing how the Milky Way is going up from the east, okay, to the west. And the first thing that we see is these two clouds here, okay? They are the Magallanes cloud, yes. Why we call Magallanes? Because Magallanes was the first navigator who saw them when he crossed the Ecuador. He came down the Ecuador, and he saw this new sky, and he saw this Magallanes, this cloud, and he thought these were clouds. We know now, thanks to astronomy, that these are not clouds, they are galaxies, two small galaxies that are satellites from our own galaxy. Okay, they're going around our own galaxy, and we can see it. Actually, are the two only galaxy that we can see naked eye, big. I know that in northern hemisphere you can see the Andromeda galaxy, but it's very small. Here down in the southern hemisphere, you really can see these clouds in dark sky, of course, as we have here in the desert. And the Magallanes cloud helps to Magallanes to find the south. Okay, remember that in the northern hemisphere you have what we call the northern star, which is pointing to the north, and which is the point where all the stars are going around in the night. Well, we don't have a bright star in the center, in the what we call the celestial southern pole. So what Magallanes did was find a way how to know where the south was. What he did was he make a triangle. He take the large Magallanes cloud with a small Magallanes cloud and make a triangle, an equilateral triangle, equal triangle. And this point here, this angle of the triangle, is the southern celestial pole. Around this point, all the star goes around, okay? And that way, if you find this point, you can take a line to the ground, and you will know that down here is the the geographical south, and this is the southern celestial pole. Also, in southern hemisphere, you can find the what we have here is the Southern Cross constellation. The Southern Cross constellation also help us to find the south. How? Well, this is the cross, first the long stick and the small stick. And the long stick, what you do is you virtually make it 3.5 times bigger. That means 1, 2, 3.5 over there, and you get in the same point where the Magallanes clouds point with this equilateral triangle, the southern celestial pole. So that's let you know, just in case you come to Chile and get lost, just look for the sky, look for the stars, and the star will guide you. Anyways, also let you know that in Chile we have, not in Chile, but in the Andes and the whole Latin America, we have a very important culture before the Spanish came, and they were great astronomers too. They have this Milky Way, okay? And the Milky Way is so bright in a night like the one that they took this picture, that is look like a river. Actually, for them was a river. The Milky Way was a river where many animals came down to take water. For example, here you can see the head of a llama. This is the head of a llama, which is coming to drink water in this river, which is the Milky Way. This is the Alpha Centauris, okay, and it's the eye of the llama. Also, we have here what we call the Coolsack in the Western civilizations, and for them, this was a bird, okay, the bird constellation. They made this constellation from this dark spot in the Milky Way. How come that we have this dark spot in the Milky Way? It's because these are cloud of gas and dust, very dark, very strong, that doesn't let the light from the star behind the cloud to get through the cloud. So what we see here is this dark spot, and for them, there were their constellations. We call them the Andes constellations, and also we can have the snake constellation, the wolf constellation, and other animals, all part of their culture. So in Latin America, we also have this great culture, which were also great astronomers in Latin America. All right. I don't know if so far there is a question. We have to go back. I think to the tour.
We don't have any question, but remember to people, leave your comments. Remember is every week we can have a virtual tour about La Silla and Paranal in English and Spanish too. So remember, you can leave question, greetings whenever you want about about astronomy, the telescope, or for the sky whenever you want. So remember this. On any things you want to search, you can go to the ESO.org to to find more information about the ESO.
Yes, you will have all this information that we already give to you. All the picture. Actually, these pictures, very few of the thousand of pictures and videos that you can reach in our webpage, eso.org, and also you can download all of them for free and in different formats. So we encourage to go to our webpage, also to follow us in the media, in our social media, in Facebook and in YouTube. One more thing before we continue here. Let me show you. Down here we have the Pleiades, okay? Subaru in Japanese, okay? This is the Pleiades for those that know the sky in the northern sky. The Pleiades, you also can see it from the northern sky. They are an open cluster, very young stars, 100,000 years only of age. All right, and here also, for those that know the northern sky, is the Taurus constellation. Okay, this is the eye of the Taurus right here, Aldebaran, and then we have one corner of the Taurus and the other one here. This is the constellation, Taurus constellation. All right, we have to go, so let's go back to the daytime platform. And before we go, we want to show you something very special here in Paranal. We are, as everything that we have seen here is from the platform, 2,600 meters above the sea. By the way, we cut the mountain before to build we cut 28 meters of the mountain before to build the telescope. But down there, about 200 meters below us, is the the camp, the base camp. This is the base camp, and here we have a warehouse, and also here is the gym where people goes in the day to make some sport, and also we have the mirror handling, or what we call all the building where we take the mirror. The mirror, remember, that has this aluminum layer that we have to change every 2 years. So we take the mirror from the telescope from the top of the mountain down here. We take out the old aluminum in this building, and we put a new aluminum surface. To do that, we have a vacuum chamber where we put the mirror without the aluminum, and then we put a new aluminum layer over the mirror. That's a very dangerous task and take about 10 days to do it. And I cannot let you go before to show you this building. This is the Residencia building. It's where people live during the day and night, and here they rest, eat, sleep, etc. And as you can see down here, over there is the where we were, the BLT platform, and the building looks like that is underneath, but it's not. Okay, it's not underground. We walk down the hill to go inside of the Residencia. It's a very famous building because the company that designed the building, the architecture company, already has won some awards around the world, architecture awards. As you can see, it's a beautiful building. We have this green, which is very important for us because people that live here, that work here, stay until sometime 14, 15 days. They make shifts 7 by 7, so they have to see green. Everything outside is earth, is desert, so a human needs to see greens and also water. How this pool, and this give us, when you are living in Paranal, give us some humidity to your skin. Okay, there is no, it's very dry outside, so it's very good because when you get inside of the building, you get this humidity into your skin. You can see green, and you can take a swim also, of course, in the pool. This building has 108 rooms, and also people here has the canteen over there, okay, the cafeteria, and where the people eat and where the people have lunch, and also all the rooms are in this side in front. They have 4 levels of 808 rooms, and here we are in what we call the lobby of the Residencia. Well, I think there's, I don't know if there is any further question. Before I forgot, what is this? This is a curtain. We have to close this dome, okay? Do not let any light to go outside in the night. Remember that we are in an observatory, in an observatory where no light are allowed. In the night, we have to walk with small torches, small light pointed to the ground, and no light have to go out from the building. So all this dome, of course, and also the windows and the doors are sealed, closed, completely in order to not let any light to go outside. Chile is very careful about light pollution. So we have a special law about light pollution where no city around the telescope, around 500 kilometers around the observatory, have to have a special light that point to the ground, not to the sky. Also special light where you have to have the city have to have lights, more yellow light and no white light. White light is very bad, not only for the stars, doesn't let us see the stars, but also because for humans. Okay, the most important university in the world research from those universities telling us that light pollution is affecting our health, okay, and also our animals, okay, all the animals, they live, most of the animals live in the night, they have a night costumes, and all light is affecting them. So Chile is one of the countries that is ahead of taking care of the light pollution. We not only take care of our ocean, our mountains, and our air, but also of our sky. So it was very nice to have you today with us. I want to remind you to go to our webpage to get to know all the information that we have. The last astronomical news also are in ESO.org. And of course, follow us in our media, in our Facebook page, and also in YouTube. Thank you very much. I don't know if there is any last question or greetings
We have
from
a last
our
question.
people.
We have one question, and only one question today is, Hi, I see a lot of air condition around the telescope. Can you talk us through the importance and how it is used? Its use?
Oh, yes, yes. Thank you very much for this last question. Um, the telescope in the day, we have to cool down the telescope, the dome inside of the dome, okay, the air inside, because if we don't do that, if we do cool down the dome, we will have very warmness inside the dome. Will be heat, will be hot inside of the dome. So in the night when you open the dome, that hot will go outside and will smash again the coldness of the atmosphere around the dome, and that will produce turbulence. The light that we're waiting with our telescope, with our mirror, will have to go through that turbulence, and that turbulence will produce distortion in the light. So our image, our data won't be as good as we want. That's why we avoid to produce any distortion around the dome. Okay, artificial, but that would be artificial distortion because we're producing with the heat that is inside of the dome. That is why we cool down the dome during the day. Actually, we keep inside of the dome during the day the same temperature the night before, the outside night. In that way, we equalize the temperature inside and outside. That's the reason. Very good question, and that's why also because we are in the desert, and because there is in the high atmosphere we don't have any distortion or very few distortion because the atmosphere do not have any water. Well, thank you very much for watching us today, and we hope to see you next Saturday with La Silla virtual tour. Thank you very much, and see you next week, next Saturday.
See you later.